All right, lecture 8 today. As usual, is a mix of topics, though we can review some old topics and do some new things. Sinusoidal modeling. At the beginning today, I want to show you something that I kind of had some fun with yesterday, trying to do somewhat serious modeling, you might say, with sinusoids. Polynomial functions, power functions, rational functions in lecture B, continuity, and limit at a point are subjects of sections 1.7 and 1.8 that we'll get into in more depth today. I do want to start by showing you how to use manipulate in Mathematica so don't forget about that. So on your graded assignment for next Monday, you'll have to use manipulate to make a plot. I like the way this window looks. As a parameter varies. So for example, if you want to plot, say, the x cubed function, here is basic syntax that will plot the x cubed function for you, and it will pick a vertical window for you. Okay, there's the x cubed function. Again, if you add in a plot range in there, comma, plot range, capital P, capital R, arrow, and then go say, negative 10 to 10, then you can pick the plot range instead of Mathematica, and the plot does then look different because you pick a different plot range. What do I mean by animation? An animated graph like I often show you on PowerPoints. I mean to add in some sort of animation parameter, you might call it, plus C here, for example, that will cause the graph to move, say, up or down as C changes here. But if I just enter this as is, Mathematica doesn't know what C is. So nothing happens. No graph. So I have to tell Mathematica to let C vary, so I have to put this entire function, this plot function, inside manipulate with square brackets around it, like that. But then that's not good enough because it still doesn't know what C is. You see that little red arrow? I need more input here for the manipulate. I need to put a comma. These fields are separated by commas. And then a list with curly braces saying, for example, C goes from 0 to 5, say, like that. Notice the curly braces around C, comma 0, comma 5. So what that's going to do is it's going to initially give me a graph when C is 0, the original graph. But it's inside one of these animator things with a slider. I can now slide C to see the graph get shifted up. Or I can open this up and play it. You can see the graph get shifted up. It might be kind of dim. Let's make this a little bit brighter with a plot style command. Red like that will make it nice and big red there. So we can play it and see it move up as C changes. So that's the general kind of thing you got to do to make an animated plot. And it's not the only kind of animation I can do. I could add in another parameter here. For example, I could add in a plus b times x, say, where b needs to go from, say, 0 to 5 as well. And that will provide two animation sliders. C affects the vertical shift. B, because it's the multiplier of the x, it actually affects the slope at x equals 0. When b is 0, the slope right there is 0. As b increases, the slope of that's going to get higher. In fact, b does equal the slope of the graph when x equals 0. Watch it here. Increase b, I increase the slope at 0, which does affect the rest of the graph too. I can also change c. I can play both of these at the same time. I can make one of them go a lot faster than the other. Lots of different things I could do. Okay? You can make your graphs do lots of crazy looking things when you do this. So again, the key thing is the plot function here, and its input goes inside the manipulate. And you put a comma, and then you say what the parameters, C and B in this case, are going to do to make the thing interactive. Okay? Any questions about that? I'm actually going to go back to Mathematica here in a minute. Yesterday afternoon I had a little fun, but it was somewhat serious fun. I modeled day length for 2019 in Minneapolis, Minnesota, here in the Twin Cities, where we live. The raw data are in a spreadsheet. I will share that with you later this afternoon. I'm trying to approximate the day length with the sinusoidal model. I hope that makes some intuitive sense. You know, in the winter, the daylight is shorter, there's less daylight. And then as it comes towards spring and into the summer, the amount of daylight gets larger, right? Both the sunrise and sunset times get further and further apart. The sunrise gets earlier and earlier, and the sunset gets later and later. And of course, when you do daylight savings time, it just shifts it, so it doesn't affect the amount of daylight that you have. So I put it in a spreadsheet and I graphed it, and I downloaded it into Mathematica, and I tried to model it with a sinusoid. And here was the best sinusoidal model that I found, approximately. I'm not guaranteeing this is absolutely the best. Notice the formula in the typical form: a sine v of t minus h plus c. The absolute value of a is the amplitude, which is about 3.35. V is related to the period. The period should make sense. The period should be about 365, right? 365 days in a year, or if you include leap years, you might go up to 365.25 days in a year. So B's got to be 2 pi divided by that, approximately. I found it to be about this. I found this horizontal shift starting at day 1 being January 1st. And this does take you to around March 20th or so, which is essentially when spring begins. And the midline's at about 12.191. I was expecting it to be closer to 12, but it just fit better when it was a little higher. 12 hours being half of a 24-hour day. And here are the graphs that I got. A little hard to see here, but if you look closely, there's some red dots underneath this blue curve. You see some right there. A little bit over here too. Those red dots are the data points. Probably should have made those bigger so you can see them. Or the blue curve thinner. The blue curve is a sinusoidal model for that. Again, January 1st, starts out fairly low, just under 9 hours of daylight. Goes up. By the time you get it to about t equals 180 or so, which is late June, say, then you're at a peak. In daylight close to a little over 15 hours. And I did graph the residuals as well. These things are the residuals. Now, they're not random residuals. This has got a pattern to it. It's got a sinusoidal pattern too, to the residuals. That's telling you that this model is definitely not perfect. Because there should not be a pattern to the residuals. They should have a random scattering. The sinusoidal is not perfect. What's this number here? That was a measure of how good the model was doing when I was using Mathematica, and I was seeking to make this number as low as possible. This is called the sum of the squares of the residuals. Essentially, you take all these vertical distances here of these residuals, you square them, you add them up, and that's the number you get. And I was trying to make that as small as possible to make the model as good as possible. And I used Mathematica. Here's the way I used Mathematica to do it. First of all, I had my, well, you know what? I'm not going to be able to use the code here because my raw length of data file's in the wrong path here. Oh, I should have just put this in here ahead of time. Okay, I'll have to show you next time. But I did a big, long manipulate here to essentially allow myself to change A, B, H, and C until it looked like I got a good fit. So it was an animation, just like with manipulate, just like I showed you a few minutes ago. And I was trying to adjust the amplitude, the period, the horizontal shift, and C, the vertical shift, to try to fit the data. I should have just had the data in here before class. I can't do it today because I don't have the data in here, but I will do it on Friday. Okay? That was my fault for not doing it. But I hope you get the big gist of it. So this is an application of pre-calculus. You're trying to use these elementary functions like trig functions to model data model. Is it really an application of calculus? Yeah, because calculus does relate to optimizing things, and in particular minimizing something like a sum of squares or residuals. Calculus can help you figure out how small this number can be. Okay? And it's complicated in this situation, but it's possible. Let's quickly review inverse trig functions. Just in terms of the graphs mostly here. Just to review some concepts. I'm not going to use these today. So what is the inverse cosine function, for example? Well, the cosine function in and of itself is not one-to-one. You might even say it's infinity to one. For any given output, like 1/2, say there are infinitely many inputs that get mapped to it. Because the graph goes on and on for the same pattern forever and ever in both directions. So any horizontal line goes through the graph infinitely many times, if it goes through the graph at least once. So it's not one-to-one, therefore it doesn't have an inverse. However, we have an inverse function that we use on the calculator, inverse cosine. So what was done to make that function? The domain was restricted. To this domain from 0 to pi for x, that piece of the cosine graph that's more bold-based is one-to-one, if you ignore the rest of the graph. So it's got an inverse, and that's what the inverse cosine or cosine function is defined to be. Graphically speaking, you reflect the red graph along this 45-degree line, you get this blue graph. That's what the graph of the inverse cosine function looks like. And you can see its outputs are between 0 and pi, 0 and 180 degrees. You always get an output in the first or second quadrant if you're thinking of the output as being an angle. You might be confused by that, like, but where's the angle? It all depends on just how you're thinking about it. You can think of the output as being an angle if you want. It's helpful. That's the purpose of using the unit circle definition. For the inverse sine, we restrict the domain in a different way. If we went 0 to pi, it would now be 1-to-1. So instead we go negative pi over 2 to positive pi over 2. That red piece of the sine graph is invertible. It passes the horizontal line test. Reflect it across the line y equals x. And you get this blue graph. That is the inverse sine or arcsine function. And for arctangent, inverse tangent. The tangent function is also periodic with vertical asymptotes. It's these red pieces here. Take the one that has a domain between negative pi over 2 and positive pi over 2. That bold-faced red piece is 1-to-1. Invert it across the green y equals x line to get this blue graph. The inverse tangent function has a domain equal to the entire real number line. You can plug in any number to the inverse tangent function. Not the inverse cosine and inverse sine. Those have a domain from negative 1 to 1. But the inverse tangent is defined for all real x. The outputs, though, have to be between negative pi over 2 and positive pi over 2. This has got horizontal asymptotes. One at positive pi over 2 right about there, and one at negative pi over 2 right about there. Okay? So it gives you both inverse sine and inverse cosine give you outputs that are in the first and fourth quadrants if you imagine them like the angles. All right, let's get into more detail about polynomials now. So I'm going over the slide that I went over briefly at the end of the last lecture, though I added the details in that I added on Monday evening. Here's the general formula. When you assume the degree of the polynomial, the highest power is n. That's the formula. N has to be a non-negative whole number. 0, 1, 2, 3, 4, 5, 6, etc. It cannot be a fraction. It cannot be a negative number. It cannot be an irrational number like pi. And it is assumed there are no higher powers of x when I write this. And it is assumed that this term really is there. In other words, an is non-zero. Otherwise, you wouldn't write it. The other a's can be 0. But the leading coefficient is called, that one right there, must be non-zero. Otherwise, it would not be 3n. Remember, I said factoring, in general, is a very difficult skill. And we don't really focus on factoring in here. Factoring used to be a bigger deal back when I was your age. There are a whole bunch of techniques for factoring. Not only quadratics, but even cubics and fourth degree. Though you should realize that those techniques are very specialized if you ever learn about them. They only apply in certain situations, and in fact, you might say just in textbook problems. If you try to apply them to real-life problems, they rarely are applicable. So you pretty much have to rely on technology when you're talking third, fourth, fifth, sixth degree, etc. You pretty much have to rely on technology. Factoring is difficult, though you can factor theoretically, which I have at the very bottom here. Yeah, okay. I'll get to that. Factoring polynomials, while always theoretically possible, is typically pretty difficult to do unless it's a cookbook, textbook problem, or a problem on an exam, where I'm making the problem in such a way that you can actually factor it. But it's typically pretty difficult. Even with quadratics, it can be difficult. It's always theoretically possible. You can always use the quadratic formula to find the roots. And therefore, you can always factor it. Let's do one where the roots are irrational. This quadratic, for example, has irrational roots. If you set it equal to 0 to try to solve for the x-intercepts, you'll get irrational numbers when you use the quadratic formula. -1 plus or minus the square root of 1 minus 4 times 1 times -1 over 2 times 1. There's the quadratic formula. It gives you -1 plus or minus the square root of 5 over 2. And the square root of 5 is irrational. You cannot write it as a ratio of two integers, two whole numbers. So these are irrational roots. And so you can't factor this in a typical kind of way, but you can actually still factor it in a more, well, theoretical way. This is not really super theoretical, but I can still take x minus the roots in each case. And that technically is an okay way to factor. You could write -1 plus square root of 5 over 2 here, and you could write -1 minus square root of 5 over 2 here. And you can check this. You can actually FOIL this out, and if you don't make any mistakes and you simplify, you should get this. The square roots go away. Okay, I'd encourage you to check that after class. So it's theoretically possible, but practically it's difficult, and you may not realize that that's possible to do, even if you can use the quadratic formula, although I'm telling you it is possible. A degree n polynomial always has n roots, actually, if you include complex number roots and if you count roots by their multiplicities. So we're not going to be using complex numbers in here. Maybe you've learned about it before. They are actually useful, as I mentioned a week or two ago. If you take differential equations, they're actually useful in that class. Paradoxically, complex numbers make some calculations simpler, including in differential equations. Also, if you count by the multiplicities, you're going to have n roots. The number of real roots must always be less than or equal to n, and it definitely could be strictly less than n. If you have a degree 5 polynomial, you could have, for example, 3 roots. Here's the general factored form. If R1 through Rk are the roots, with multiplicities m1 through mk, and if an is the leading coefficient, you can factor it like this. These r's could be complex numbers. Okay? Just some information for future reference, just in case you ever need it. And you might, if you're physics or engineering, you will need to use complex numbers. Okay? So, especially for those majors, it's good to realize that theoretically you can factor it like this. You know, typically with most examples we do, the m's are 1. And so that you would have n factors here in that case. All the multiplicities are 1. They're called simple roots. I think I called them ordinary roots last time, but more technical term is simple roots. The m's need to add to n, and usually all these m's are 1. What else do we want to know about polynomial functions? Well, as far as skills go, given a graph, you should be able to find a formula. So if I have a graph, let me just draw an x-axis, that looks like this, for example. Or maybe this is -3 and this is 7. You should be able to find a formula for that. Or a possible formula, especially if you also, I guess I will draw the y-axis in here, if you know its y-intercept as well. Let's say the y-intercept is, oh, I don't know, 100. These things typically grow pretty fast in certain ways. What would the formula for f of x be? Some constant a that you have to figure out based on the y-intercept actually. One root is at -3, and it looks like a simple root because it's just crossing the x-axis in an ordinary kind of way. So put an x plus 3 here. And then the root at 7 looks like a double root, root of multiplicity 2, because it's tangent to the x-axis and it looks kind of like a parabola. So you want a factor of x minus 7 squared. To find a, use the fact that f of 0 is 100. -7 squared is 49. 49 times 3 is 147. A would be 100 over 147 for this example. Then you should be able to multiply this out. I'm not going to take the time to do that. But you should be able to expand that out. With this part, you would FOIL, and then you'd multiply it by x plus 3. Actually, let me go ahead and just expand out the part that does not include the a. I'll put the a in front here. I guess I should do this. If you square x minus 7, think about FOILing. X minus 7 times x minus 7. First times first is x squared. Outside and inside products are both -7x, combining to give you -14x. And then -7 times -7 is plus 49. To do this multiplication, multiply the x times every term, add the results, multiply the 3 times every term, add the results, and then combining like terms. X times x squared is x cubed. X times minus 14x is minus 14x squared. X times 49 is 49x. I could continue to the right here. I like lining up the next set of terms below, lining up like terms. 3 times x squared is 3x squared. Put it beneath the other x squared term. Plus 3 times -14x is minus 42x. Then 3 times 49 is plus 147. I'll go ahead and plug in the a. 100 over 147 times in parentheses x cubed minus 11x squared plus 7x plus 147. Then if you like, you can distribute the 100 over 147 through. It would cancel with this one, it would leave you 100, but you'd have fractions in front of the other terms. Is there a question over there?
When do you expand it, when do you not?
It depends on if you're told to expand it or not. If I say expand it, then expand it.
Because I know in the book it didn't have it.
Yeah, I think leaving it in an unexpanded form certainly saves time and work and is easier to understand as far as the answer goes. But if you're told to expand it, you should be able to. Did you say the book's answers were in factor form or not?
They were, yeah.
Okay. That's easier to understand. More on polynomial functions. The number of turning points, also called local extreme points, where you have a peak in the graph or a valley, is at most n minus 1. With this graph here, there's 2 turning points, right about there and right at 7. I'm not sure exactly where that turning point is, and I can probably use technology to try to estimate it. Actually, calculus methods with derivatives can help us figure it out, we will see. But there's 2 here. This is a degree 3 polynomial. It can have at most 2 turning points. Some degree 3s have no turning points. They look like this or like that. They have at most n minus 2 inflection points where the graph changes concavity from a frown to a smile or vice versa. And this one looks like a frown until right around here, inflection point right around there, and then it looks like a smile thereafter. Looks like it has 1 inflection point. These also have 1 inflection point. We'll learn more about both turning points and inflection points as we get into derivatives more. Their limiting behavior or end behavior can be described quickly this way. In cases, first of all, if the degree n is odd and the leading coefficient is positive, then this is true. The limit as x goes to plus or minus infinity of this polynomial is plus or minus infinity, where the plus infinity here matches with the plus infinity over there, and the minus infinity here matches with the minus infinity over there. Degree, odd degree means the graph either looks like, in the end, I'm going to do a little dance for you here, it either looks like this or like that. This or like that. I'm so glad I'm not falling down. It's a little dance, okay? That's the n equals odd case. The plus infinity over here goes with the plus infinity over there. The minus infinity goes with the minus infinity. I guess when I write it like this, then the an is positive. If an is negative, that's the other case. That's doing a little dance like that. When an is negative. Notice I got a plus or minus infinity there and a minus plus infinity there. The plus infinity here goes with the minus infinity over there, and the minus infinity over here goes with the plus infinity over there. It's like this, okay? Going to minus infinity as x goes to plus infinity. Going to plus infinity as x goes to minus infinity. When n is odd and n is negative. So the oddness or evenness of the leading of the degree, and then the sign, positive or negative, of the leading coefficient determine the answers. If n is even and the leading coefficient is positive, then you go to plus infinity. Either way, it's like a touchdown. Okay? When n is even and an is positive. And when n is even and an is negative, then it's take your touchdown symbol and move it upside down. Okay? These are just fundamental things you should know. You should realize and use whenever you need them. Based, helping you find formulas for graphs. I do see the end behavior here. Goes off to plus infinity that way and minus infinity this way. I know it's got to be a cubic with a positive leading coefficient. Actually, a 5th degree, a 7th degree, a 9th degree could have a graph that looks like this as well, though it would be probably a little flatter here at 7. If I made it a multiple root at least. However, it's simplest to go with a cubic. Okay? It doesn't have to be flatter. But if I made 7 a multiple root, like a root of multiplicity 4, then it would be flat. Dominance. Higher degree polynomials with positive leading coefficient grow much faster than lower degree polynomials with positive leading coefficient in the long run, as x gets bigger and bigger. The higher the degree polynomial is said to dominate the lower degree polynomial. As x goes to infinity, I probably should have added. This is true even for seemingly extreme situations. This came up in the homework. For example, 0.00001 x to the 4th dominates 100,000 x cubed as x goes to plus infinity. If you graph these in the same picture in the calculator or Mathematica, it's going to seem like this one's dominating. It's going to seem like that one's growing faster. But if you go out far enough to the right, maybe x has to be millions or billions or trillions, eventually this 4th degree, because it has a higher degree, is going to go higher than this one. We can even set these equal to each other and solve for x to figure out where. I don't want to take the time to do so. That would be a good exercise for it. Set these two things equal to each other. Figure out then where they cross. It's going to be at a big value of x. They do cross at x equals 0 as well, but we're worried about the big value of x where they cross. They will cross. This one will eventually get higher faster, eventually in the long run. They're defined for all real numbers. They also are continuous and smooth over the entire real number line. Okay? The domain is the set of entire real numbers. The graph is continuous, no corners in the graph. Well, no breaks in the graph, and smooth, no corners in the graph. I often see people when they're sloppy drawing quadratics, when they're connecting the points, to maybe draw them like this or something. Don't do that. Plot points and connected dots. Don't make it look like that. That's wrong. Make it smooth. You're in too much of a rush if you're doing that. And the subtlety is important, actually. Make it smooth. That's an important thing in calculus.
What is there a cost?
We'll see examples of today of some functions with cusps here after the quiz. In fact, maybe even now. Power functions. What are power functions? These are analogous to the leading term of a polynomial function, though we do allow arbitrary powers, including negative fraction and even irrational powers. Here's the formula. That's called a power function. A times x to the p, where we're implicitly assuming a is non-zero. The p equals 0 case is not very interesting. That would be essentially a constant function at a, even though technically 0 to the 0 power is undefined, but don't worry about that. We just assume a is non-zero. But there's no other terms. But the p could be negative. It could be a -2, for example. It could be fractional. It could be 1/2 or 1/3 or 2/3. These get a little tricky as far as thinking about their domains and graphs, especially when p is fractional. If you're talking about f of x equals a times x to the p, where say p is bigger than 1, the graph, if p is a whole number, will surely be defined everywhere and basically look similar to, x squared or x cubed.
How is that different than an exponential function? Are you talking about polynomial or exponential? Exponential.
Exponentials look like this.
But isn't it the same form? It's just different variables.
No, you're thinking of a quadratic maybe.
Like y equals k and x, whatever.
Y equals kx what?
So,
I can't quite hear you, I'm sorry.
never mind.
Okay. P actually has to be even here. If P is a whole number and odd, then it's more like a cubic. Let's do some other interesting cases, though. This is where P is odd. These new kind of cases, where P is, for example, a fraction. Let's go ahead and pick A to be 1. So let's look at f of x equals x to the p, where P is a fraction and rational, and say between 0 and 1. You have to be a little careful here because it's best probably to just think case by case. For example, if P is a half, then x to the p is x to the 1/2, which is the square root of x. And if we're only allowing real number outputs, the domain only consists of numbers greater than or equal to 0. And the graph ends up looking like this. That's the square root function right there. On the other hand, if p is 1/3, as another special case, then x to the p is x to the 1/3 is the cube root of x. technically speaking, that's defined for all real x, and the graph looks about like this. You're just trusting me on these graphs here. That's what the cube root function looks like. Why is this one only defined for x greater than or equal to 0, and this one defined for all real x? Because when you take the square root of a negative number, you get a complex number, in this case a purely imaginary number, 2i involving the imaginary unit, the square root of -1. And we're saying in this class we're not worrying about complex numbers with imaginary parts. So for us, we don't want to plug in negative numbers for x, because we don't get a real number output. With a cube root, however, that is defined for negative x to give you real numbers. For example, the cube root of -8 is -2. Since -2 cubed is -8. When you plug in -8 into the cube root graph, you get an output of -2. Some other kind of strange situations include the case where, for example, p is, say, 2/3. Which means either square the cube root of x or take the cube root of x squared. Those are the same thing.
Is this just like a general, because like those first ones,
Am I trying to get at generalities here? Is that what you're asking? It's hard to describe generalities quickly. So I'm considering special cases. If that is helpful.
Wait, okay, so like the fx equals ax, like those two, those are.
Yeah, I probably should have considered special cases from the start. I was kind of doing that here. I am saying p is a whole number and even, like 2, 4, 6, 8, 10. Here I'm saying p is a whole number and odd, like 3, 5, 7, 9, 11. The p equals 1 case is just a straight line. I mean, it technically follows that pattern too, but it doesn't look like that. Here I'm picking particular fractional values for p. Turns out this one has a cusp. Okay, and again, you're just trusting me on this, that the graphs look like these things. It's sort of just wanting you to know these special cases. On the other hand, when p is negative, like -1, x to the -1 power is 1 over x. That's got vertical asymptotes at x equals 0. A vertical asymptote at x equals 0. And when p is -2, for example, x to the -2 is 1 over x squared. That's also got a vertical asymptote at x equals 0, though it's never negative in value. It's more like this. We'll come back to this after the quiz. Let's take the quiz.